not too far back, but just a little bit back, and get into this idea of what mechanisms are trying to show you and how we know what they are. We don't just make this stuff up. We're not just guessing at what this stuff is. We can prove them by experiment. So we started out by thinking about the possible ways of substituting something on an sp3 carbon. And all the reactions you will see in this chapter, it's all sp3 carbon. We can say that if I want to replace the leaving group with a nucleophile, I can do it in several different ways. I could have the nucleophile come in, attack the electrophile, and boot the leaving group out. That's shown here. This is a concerted process, and we've developed this idea that it's bimolecular. You need both of those molecules in there, the nucleophile and the electrophile, in order for this to work. So that's one possible way. We'll define that again today as the SN2. Another possible way of doing this is to go for a stepwise process in which the leaving group breaks off first. Under certain circumstances that can happen. We'll see why today. If that happens, we get a slow step, which will be the rate determining step here to form a carbocation. That then is going to get trapped by a nucleophile and get overall the same outcome. You're going to replace one thing with another, but through a very different pathway. With that in mind, we had a third possibility, but we realize it's impossible. If you attach the nucleophile first and then have the leaving group break off, you can't do this, right? You cannot do this because you're going to break the octet rule, and that's not allowed. So the top two will be defined in Chapter 7 as the SN2 at the top and the SN1 at the bottom. So ideas that you really haven't seen before, but that's definitely bringing things together that we've been doing for a while now. So how do you know what's happening? How do you know it's an SN2 and not an SN1? Well, you can do rate experiments. You can do kinetic experiments, which a lot of biochemistry is about. You can add more substrate or add more nucleophile and see what happens to the rate. Does it get faster? Does it stay the same? Overall, if the rate changes when you add something, it is involved in the rate determining step. That substrate will be involved in the rate determining step. I've got more to say about rate determining steps today and Friday, but in this case, if I add more nucleophile, does it go faster or slower or stay the same? It goes faster. And if I add more electrophile, it goes faster. And if I concentrate the reaction, it goes faster because they don't have to travel as far to find each other to interact. So the evidence for this being what we call a bimolecular concerted process comes from that type of experiment, where if you add more nucleophile, it does get faster. That means the nucleophile must be present, it has to be around in that slow step. Now in the SN2 reaction so far, we've only seen it be one step, so it has to be present in that step. We came up with this definition. From that rate equation, we can say it's bimolecular. You need both pieces to be there for this reaction to go, and we came up with substitution S, nucleophilic N, and then bimolecular 2, SN2. Fairly simple. It is completely analogous to the acid-base chemistry. In recitation this week, what we did was we went through the acid-base chemistry first, defined it as a bimolecular process, drew out the transition states, drew out the mechanism for that, and it turns out it's pretty much the same as this. It's pretty much the same as an SN2 reaction. But in the SN2, we're talking about carbon, and in the acid-base chemistry, we're talking about protons. With that in mind, there is the classic mechanism for an SN2 reaction. All put together on my flashcards there, if you want to go get those, use them on your phone, whatever. And you can see now the nucleophile has to be there. The nucleophile has to attack from a certain direction, from the back. That's where the opening is to attack. And then the leaving group gets pushed out on the other side. That will have some stereochemical consequences today because we'll see this process called inversion. We'll end up now with a new product. We end up with a material now that we have produced. It could be a whole bunch of different things in which the nucleophile here has replaced the leaving group. Good leaving groups tend to be things like halides. We'll see other varieties as we work our way through 7. But this is fairly simple until we get halfway through the chapter and we start to expand the diversity of what's possible. We talked about the application of this in biology. If you take biochemistry, or if you take my biological chemistry class next year, you'll find that these are all organic compounds and they all obey the rules mostly of organic mechanisms. So we learn now the basics. What will get frustrating over this coming weekend, as you think about the exam coming up next week, is how this expands very quickly. Because I've got generic nucleophile there, I've got generic leaving group. Of course, we won't be using generics on an exam. You'll see all sorts of different varieties of this and all sorts of different types of this. If you get the basic ideas, it's all the same reaction. So we can put specifics in. We can talk about ways of turning one functional group into another. We could turn, for example, an alkyl halide here into an ether, simply by kicking out the leaving group, doing an SN2 reaction. How do we know it's SN2? Well, hopefully after today you'll see primary starter material, strong nucleophile, SN2. Tertiary system, different type of nucleophile, will be the other example, SN1. So examples from the lab, you'll do this in the near future. You can take, for example, a secondary alkyl halide here, sodium iodide as the nucleophile, there's your leaving group, and acetone as the solvent. Most times you need some solvent to make this reaction work, so the acetone there is a bit more detailed. Don't get lost with that. We will have some discussion about acetone or solvents in the near future. So we left off with this, and this is always confusing. The idea that more evidence for the SN2 being bimolecular and the direction of approach of the nucleophile being from the back is given by the fact that it's stereospecific, and the fact that you get inversion. You start out with your groups pointing in one direction, nucleophile comes in, your groups end up pointing in the opposite direction. We did this in recitation a little bit on Monday and Wednesday, and it's starting to make some sense. So this type of reaction here, you've got to recognize that this is chiral, it is secondary, it is somewhat accessible, and the nucleophile will approach from the back. If it does, what direction do all these groups have to go? In the opposite direction. They have to get out of the way because they're going to get repelled. That then results in this being attached on the opposite side to where the bromine broke off. That is referred to as an inversion, and you've got inversion of stereochemistry. Okay, so the product is inverted. In this example, it just happens to be that S turns into R. And for all the examples you'll see with me, that will happen. You will see an inversion in which one stereocenter gets inverted to the other one. But you've got to be very careful here. If the alpha D, and I've had questions about alpha D this week, so it's obviously something that people aren't quite comfortable with. If alpha D for that is something like plus 64, can you tell me what alpha D for this is? No, you cannot. It's a different molecule. It's not the enantiomer. It's a very different molecule. You don't know what that is. It's like a melting point. I could ask you what the melting point of this material is. You wouldn't be able to tell me unless you actually ran the experiment. Okay, so be very careful there. Certainly alpha D is not 0, because this is definitely a chiral material with a specific chirality, a specific configuration, and it will have an alpha D. So alpha D will not be 0. You'll see where that becomes relevant between now and Friday. It will be a number of some type. So we have now an idea that the direction of attack is important. We have to attack the electrophile from the back, and we have to kick out the leaving group from the front. And as everything else gets out of the way, that's where the inversion process happens. This has to move across, this has to move across, as does that. And you end up like an umbrella in the wind. It gets knocked from one side to the other. Here's the sort of chemical physical idea of why this has to happen in this direction. This is where you can develop a bond. That's the only place where you can put electron density into the anti-bonding orbital. So now we can decide that attack from here is no good, because we've already got electrons there, and attack from here is good because that's a vacant space where I can deposit electron density. So every SN2 reaction occurs with inversion and attack from the back of the molecule. Everybody okay? Okay. Now, this isn't going to work for me. I'm going to go to plan B, and in my class often we end up in plan F or G, but that's okay. And I don't know if it's going to let me do this. Well, I need to get rid of that. But what you have here is a nice little graphic, if I can get hold of the thing, and put it on the internet. Come on. I just want to go here and it won't let me. There we go. Almost there. Okay. This will work. It doesn't want to work in my PowerPoint slide for whatever reason. But there's a nice graphic showing the SN2. Yeah? You see the nucleophile coming in, everything else gets out of the way, leaving group pops off. It's on your slides. If you want to look at it later on, go ahead. But that's exactly what's happening. And what you can see now is a definite change in the orientation of these atoms. They are going to become, at some point, planar. They're all going to be in the same plane at some point. As the nucleophile comes in with its electron pair, pushing these things out of the way, it will become planar, and this thing will start to pop off. And we'll see now the transition state for this is said to be trigonal bipyramidal. We have pyramidal arrangements of the atoms around the central carbon, and the 3 hydrogens in this case all happen to be in the same plane. Now, while I've got this up there, and it took me great pain to do so, what do you think will happen to the rate of the reaction if these things get bigger? Let's say the white atoms here get bigger, they become methyl groups or something else. What do you think will happen to the rate? Faster or slower or the same? Do we all see slower? If things get bigger, it will get slower. That's all you need to know. Yeah? Because that will then transition us into the SN1 reaction. So I go back over here, and I think about what that means. I think about, I want to do it now. God, technology, children, no. Okay, there is a depiction of the transition state for that process, if you like, in the middle. A transition state has to live in these square brackets, that's the definition, and we have to use this double dagger symbol to say that it's a transition state. And we can see now direction from attack from the back causes everything else to get out of the way. And that then is a sort of a planar arrangement of those 3 groups. And I have to use these dashed lines because they're not full bonds. I'm forming a bond and I'm breaking a bond, so I have to use the dashed lines to say so. And I have to be very careful about assignment of charges, because that transition state will not necessarily be neutral, because I'm mixing a negative thing with a neutral thing. So why am I using delta negative here in the transition state? Well, that's because I'm losing negative charge from the sulfur. And what you need to do for these more complex examples is look at what we start with and what it becomes. It starts out negative, it becomes neutral. You have to go through delta negative to get there, right? You have to go through something that's a little bit less negative to get there. And I have a delta negative on the BR because it starts out neutral over here and it becomes negative over there. It's becoming negative, therefore we'll use delta negative to describe that. When we get into the SN1 reaction, we'll have to use delta positive. In this case, no, we don't need to use that. So I have a picture here, which is said to be trigonal bipyramidal, and that is an accepted transition state for the SN2 process. It tells you a lot. It tells you the direction of attack here, it tells you the direction the leaving group is breaking off, and it shows you the inversion process. Go ahead. Attached to the same molecule at the same time. If you're breaking the octet rule, no. Yeah, if you're breaking the octet rule, no. But there will be an example, the SN1 reaction, in which the steps are different. Yeah, but this time, everything's happening at once. It's said to be stereospecific. What that really means is that if you start with one configuration, you get the opposite configuration, because you get an inversion process, right? So the outcome, the stereochemical outcome, depends upon the stereochemistry of what you start with. In other words, if it's simple and you start with S, you will get R. If you start with R, what will you get? S. That's stereospecificity. Okay? So be careful here. We've got to think about rates of reaction. We've got to think about the factors that are going to build into why something gets slower, why something is faster than something else, so we can get into more complex examples. So these types of charts tend to be a bit cluttered. There's a lot going on there. But essentially all this is the question I just asked you. What will happen if you start to put bigger groups around that carbon? It will get slower. So I have on the left here methyl bromide. No real bulk around that central carbon. Don't forget the context here. We are attacking this carbon. That carbon's very easy to get to because there are no large groups attached to it. As I move from left to right, and I go to the primary system in which I replace one of my hydrogens with a methyl, that methyl is bigger. It will get in the way as we try to attack the central carbon, the alpha carbon. And so this will be slower. If we use the secondary as our sort of standard, a rate of 1, well, it turns out primary systems are about 100 times faster, typically, because they're more accessible. And the methyl group is greater than 1,000 times faster because it's very accessible. But things start to slow down as you hit the secondary systems in the SN2 reaction, because the rate determining step, the overall step in the SN2, requires that nucleophile to get to that carbon. If we can't get to this carbon, it starts to slow down. And in the bigger picture before the exam, which isn't too far away now, there will be a big shift, a big change when we hit there. Because we get to the tertiary systems, and all of a sudden they become too slow to be effective, or even too slow to measure. Colleen? I can't hear you. No, don't forget, slow means the height of the barrier. We're not talking about where the product is yet. We're talking about the height of the barrier. The height of that barrier is too high that this reaction won't go. And the reason I have my red line there is to show you it has an alternative pathway to go to get to the same place. So it can't do the SN2, it'll go someplace else. Michaela? No, be very careful here. I'm going to say this again, right? There's no rearrangements here. Rearrangements only happen with carbocations. This is all about how big the groups are close by. So it's nothing to do with how reactive this is, it's how to do with how big that is. And we've heard that many times, right? In acid-base chemistry, sometimes it was to do with the size of the anion. It's very difficult to keep all of this stuff straight unless you keep at it. Because people start doing strange things and start to bring in pieces of this chapter and this chapter and this chapter, and it doesn't make any sense. So the idea now is that this is fast because it's accessible. That's the key word there. It is accessible. Over here, this one is getting less accessible, and over here, less accessible again, and over here, less accessible again. Playing with our phones, we're not going to be friends. That's okay? All right, moving along. So crowding in the electrophilic or the electrophile slows down the SN2. And that can be taken further. Anything that's local, anything that's close by, that's going to crowd things out, will have an effect on how fast that thing goes. So here now, bringing together, this is on my set of, what do you call them, flashcards if you like, is a summary of what we just did. We said that an SN2 reaction involves some nucleophilic species going after some electrophilic species, and as long as that electrophile is accessible, we'll get an SN2 in which both of those pieces come together and ultimately end up with a product that's inverted. Now, every SN2 gives an inversion. Sometimes you can't measure it. Why can't I measure the inversion in this process? It's not chiral, okay, but it is happening. Every time it's happening like that. So I get swapping of one group for the other, and I end up with a product. And that product then will have some use later on. To start off, let's think about this picture again so that we understand the language. How fast things go is this factor here. How high is that barrier? All right? How high is that barrier? And then in terms of the overall reaction being viable, in this case it turns out the product is more stable. So what is K? Greater than 1 or less than 1? Greater than 1, the product should be favored. Go ahead. Yes, I mean, you think about quiz and homework type stuff, yeah. So it's the difference here in energy between those two places, those two horizontals. That's right. Go ahead. Well, when you're trying to draw these transition states, which we can do again in recitation, right? I don't know how well you can see this at the back, but I'm holding my hand up, right? Can we see this at the back? I have a hand. I got two of them, in fact. Okay. Johnny, which direction is my thumb pointing? Towards me or towards you? Towards you, right. So my thumb is over here. If he can see it, everybody else can see it. My thumb's over here, pointing towards me. When this inversion happens, my thumb is now over there, but it's still pointing towards me, yes? So it's still a dash as far as you're concerned, it's still a dash as far as you're concerned. It's consistent. You just have to be careful and practice that. So there is the classic transition state, the classic picture for all of the bits and pieces of the SN2 reaction brought together. There's my picture again showing how this happens in reality. It's not going to work now, but you know what it's about. So we can talk about relative rates of reaction. And this is simple as it stands, but as we get into material in the near future, no, it's not simple at all, because you're trying to decide which factors apply when. That's the hard part about this class. When does what apply? So in this example, or in this slide, we have an SN2 reaction with a methyl substrate. What that means is we're dealing with something like CH3Br. And then we have a primary substrate, maybe something like that, with one carbon attached off of the alpha carbon. And with a secondary substrate, maybe we have two there. So we're getting some branching. And that branching makes a difference. So it turns out now, for those not comfortable with the transition states and with the activation barriers, this is a low activation barrier because this is accessible. The whole reaction here relies upon attacking that carbon. If it's easy to get to, it'll be a fast reaction with a low activation barrier. Here we can see a primary system. All of a sudden we started putting a methyl group there. It got bigger. And so the carbon we're attacking, which is this one, we're not attacking the methyl group, it's just there getting in the way. The one we're trying to attack is more crowded, and so the activation barrier goes up, which I think makes sense. And you go to the secondary system, and we can see now that the activation barrier is getting significantly high, and that will be the frustration as we head towards this test. Sometimes the secondary do the SN2, sometimes the secondary do the SN1, because they have the chance to do both. Why not put a graph here for the tertiary? They can't measure them, right? They don't do SN2 because they do something else. So this should make some sense now. If you want to do an SN2 reaction, a methyl group is really fast. Primary is slower, but still viable. Secondary is slower, but still possible. And tertiary isn't going to happen for the SN2. That's a general rule. You can expand this. You can extrapolate this. You can start talking about local effects. You can start thinking about taking this steric bulk someplace else and seeing what effect it does. So you have an experiment here where you have 4 flasks, one of which is a primary alkyl halide. In fact, guess what? They're all primary alkyl halides. Yeah? The actual bromine is attached to a carbon, which is primary. So we're not changing the steric environment at the electrophilic carbon now. We're changing the steric environment next door. Now, what's happening here is quite a dramatic, and if you don't like these numbers, don't do engineering, don't do PChem, don't do biochemistry, right? Because these numbers are dramatic and they tell you stuff. This is the basis of what we're doing here. Ethyl bromide is measured as 1. If you put one methyl group in place of one of these hydrogens, it's not too different, but it certainly is slower. If you put 2 alkyl groups here, and this is not isopropyl, this is not right at the electrophilic carbon, this is next door. The nucleophile still has to come from that certain direction, and it's going to hit this material. So I'm getting an order of magnitude here, decrease. And if I put this big group here with 3 methyl groups replacing each of these hydrogens, it's gone down to a ridiculously slow rate. So what that tells you is, yes, Primary, secondary, tertiary makes a difference, but even within primary systems, if you have stuff next door, it gets in the way. And it can get in the way to the point where it's, thousands and thousands of times slower. You'll see that in biochemistry. That's how you can tune things in biochemical systems, by being very subtle. So that will have an effect on the SN2 reaction, and there's a picture to show why. All of this material, this one over here is this one down there. You have this big T-butyl group next to the alpha carbon. Don't forget, I'm trying to attack here, but that stuff gets in the way. And that stuff then slows things down. If my nucleophile is trying to get in, we're going to see steric problems right there, and you see the difference in the rates. So it's a general thing. If you start taking that material further and further away, it won't have as much an effect because it's not so close. But certainly at the alpha position and next door at the beta position, it makes a big difference. Anybody? Hello, Brienne. Now, okay, this is not a criticism. Let's be very, very careful with the language that we use, because rearrange means something specific in they have to move. They have to get out of the way. Go on, carry on. Well, basically, okay, so basically, ready with my thumb again, Johnny? Right, it's over here. My thumb now is a huge, great big T-butyl group. Right? If it comes in like this, it's going to go over there. It's still a big, huge T-butyl group. It just moved its direction in space, the same way the other groups did on the previous slides. So the whole point of this is SN2 are governed by steric environment, and even if you put something next door to where you're trying to attack, it makes a difference. It gets in the way. Okay, examples. And this is where you really need to be on top of things. If you're doing your physics homework, this isn't going to work. We have secondary alkyl halides. In this example, I've given it a chiral system. This one is definitely RRS. And what we've done here is mixed it with something nucleophilic. How do you know this is nucleophilic? Well, I just told you. And you've got Na plus and you've got N3 minus. The reason you know it's nucleophilic is it's negative. It's the negative part of the salt, okay? The anion then. So I'm going to do a nucleophilic attack here where I attack the bromine and I kick it out. Now, why has this become a dash? Why has that become a dash? Because of the inversion, because of the fact that we had to attack from the other side. So in this case, the leaving group is a wedge. That becomes a dash. We have a lot of stuff to cover in this chapter. I'm on slide 40 of 97, right? Between now and probably next Monday. There's an awful lot of detail here. So the solvent we haven't talked about yet, but you'll need something that's appropriate, something that dissolves both of these things up, and that's a bit of a challenge. From your vast experience as organic chemists, is that polar or non-polar for the most part? I think it's non-polar, right? Is this salt polar or non-polar? Anybody want to hazard a guess? A salt polar or a salt non-polar? Oh, thank you, thank you, thank you. I can sleep well now. Right, that is superpolar, that's pretty non-polar. You have a compatibility issue. You're trying to mix these things up. If you add water to this system, yes, it'll dissolve the salt up, but it won't dissolve the organic stuff up. If you add hexane to the system, yes, it'll dissolve the organic, but it won't dissolve the water. That's a big chunk of stuff to come probably on Friday when we talk about the how to run these reactions. So we are putting in more detail. We can do this with other more complex systems. What do you think the effect of this will be? If I ran this reaction with simply bromocyclohexane, will this reaction be slower or faster? Slower. Why? What will the effect of this stuff be? Gets in the way, slows things down. Subtle things, but you need to understand them. Again, I'm getting a change in the configuration there. Why is that a wedge where I started with a dash? Okay, nucleophilic attack comes in from this direction, from the front, kicks that out from the back. This ends up as a wedge. Joe?
So the bottom line structure never changes because it's represented as 20 nanometer transition states, 315.
Yes. Dobson? Sure, sure, unless they don't. This is where the study comes in, right? When we started doing RNS and we said, okay, everything seems to shift or move, or imagine when we did fissure depictions where I had you go from a fissure to a wedge dash, and the engineers aren't in recitation, we spent hours on that, right? You are now very confident doing that, so you should be okay with this, unless you're not in recitation. But you will be next semester because I have an extra one, just for you lot. Okay. There's another example. Primary system. We have a delta plus here, if you like. We have a negative piece here, and nothing more complicated than high school chemistry. Sodium's positive, what's next to it is negative. The negative bit is the nucleophile. Goes after this, kicks it out, breaks this up. Why no need for wedges and dashes here? It ain't chiral. Okay? It's a primary system, so there's no chirality. You will, by tomorrow, I hope, be comfortable with what this means. So I've spent a fair amount of time talking about a biomolecular process. And now we have to transition into the other one. And the other one is much more complicated because it involves intermediates, it involves multiple steps, and it involves rearrangements. And this is the SN1. The SN1's all over the place as you're chewing food up, as you're getting food hydrolyzed in your gut. The SN1's happening all the time, so we need to be comfortable with it. The SN1 is the other pathway. So I usually go up 11, but for, you know, if you've been on 224, they're fixing that bridge on 224 at the Camfield end, right? And today they were putting the last layer of the asphalt down, and 11 North was stuck. I couldn't get on it. So where do I go? I go home. No, I can't go home because I have to come here. I go up Market Street. So I have an alternative pathway because one pathway was blocked. And that's what's going to happen now. We just said that a tertiary system won't do an SN2 because it's blocked. There's too much stuff in the way. But you still can get to where you want to go. You can still get a substitution product by taking an alternative route. In this example, the S1 mechanism. The S2 mechanism was bimolecular. Both the nucleophile and the electrophile were involved in that step. Here, I'm talking about a process in which a tertiary molecule will collapse. It will break apart into two pieces. And it will break apart with a leaving group coming off, and after that we produce this. And we have seen a bit of this so far. We have seen positive charges on carbon. They're allowed because of the fact that carbon isn't so highly electronegative. It will be okay with this positive charge. And then we have to understand, what is a positive charge in reality? It's an empty p orbital, right? It's an empty p orbital. That will mean something very soon now when we talk about stereochemistry. But this isn't particularly happy. Why not? It's only got 6 electrons. That 6 electron thing needs some help. I've got some nucleophilic species floating around waiting to help. I do my nucleophilic attack. I get back to something stable. So this is fundamentally different to the SN2. It's a very similar outcome, but the stereochemistry will be different, and the way you set it up is different, and the substrate is very different. So I have here, what type of alkyl halide is that? Soccer team. Are we awake? Come on, we want to win. At least once this season. Is that a primary, secondary, or tertiary alkyl halide? That, I'm asking you. Take a vote. There are 3 of you. Guess what type it is? Oh, bloody hell. 3, tertiary. Right? Tertiary. It's a tertiary system which is very crowded. So that's not going to do an SN2. This is why it switches to SN1. So we're particularly looking for systems that are good at forming carbocations. Now, be ready, Haldeman. What type of carbocation is this? Tertiary. So what do tertiary carbocations benefit from more than secondary or primary? Oh, you disappoint me. What stabilizes the carbocation? Hyperconjugation, which is, have another go. Oh, dear me. Anybody, hyperconjugation. That's it, sharing electron density from where? Adjacent sigma bonds. So this guy here will be okay. It will not be stable. It will be high on the graph, but it won't be unachievable. And it's a tertiary, and it's got 9 of these CH bonds to help out the central carbon. So we'll mention hyperconjugation again. Absolutely fundamental principle that you needs to stick with you all the way through the terms. So that carbocation is okay. It won't live very long because it needs some electron density, and away we go. And I'll mention this now, and I'll hopefully hammer on it in a few minutes. If this carbon on the left-hand side is inaccessible, and I can't attack it directly, why all of a sudden is it okay to attack this thing in the middle? That's well done. It's planar. It is flat. You got rid of all the stuff pointing in the wrong directions and pointing out because it went flat. That's absolutely key. That carbocation is flat, and it will be fast to attack because it's flat. There's nothing getting in the way. So let's think about where we go. What's the hybridization pattern here? sp3. What shape? Tetrahedral. What's the hybridization pattern right there? sp2. What shape? Trigonal planar or flat. That's key. So we'll see examples. We'll see different nucleophiles, different electrophiles, and hopefully we'll get something out of this. We can take, for example, an iodide, treat it with salt, and we end up with a chloride, and sodium iodide as a product. So overall, it's the same type of process as the SN2 reaction in that you end up with the same types of products, but of course, the mechanism now will be quite different. Everybody okay? Colleen. Ah, a fine question. Right? You start to think like a scientist. The question is, why isn't the chlorine over here? If in SN2 it seems to switch places. I'll show you. The SN1 is different stereochemically. It's quite different. And in this example, it's not chiral, so you really can't tell. But there is a definite change in trajectory of the nucleophile in the SN1 versus the SN2. Good question. Okay. Experiments. We have to prove what we do. It's not all made up. The idea that, in this case, if you add more nucleophile, nothing happens. If you add more electrophile, it gets faster. Concentration, it gets faster. So what we need to understand here is that in the first step, and I'll show you the graph in a second, but which do you expect to be slower? Step A, leaving group breaking off, or step B, nucleophile coming in? Just think about it carefully as a scientist. A, why do we think A? Not because it's leaving, that's really just a, that's a circumstance. Why is going from here to here slow? You're going to something less stable. What type of step do you think that would be? Give me a word that describes that. It will be, but what's this fundamental word energetically? Endothermic. That will be endothermic. Down here will be exothermic, and that will be faster. Okay? So I've got now a simple idea that says this will be slow, and this step will be fast. So we'll use that term again. This will be rate determining. This will be the higher barrier. And all of my rate equations are based upon that rate determining step. So if I'm looking at this first step here, A, is the nucleophile present? No, the nucleophile does not come in until the second step, which is the fast step. So in this case, the reaction rate only depends upon this, not the nucleophile. So therefore, there's your rate equation. We'll say it's unimolecular. Unimolecular, there's your 1, SN1. In the SN2, it was bimolecular because you needed both those things to be there in order to make this work. Is everybody okay? Falling asleep over here. Don't wake her. Okay. There's your rate equation. There's your definition. Substitution by a nucleophile, unimolecular. So this number, whether it be 1 or 2, comes from that graph. It comes from the rate determining step in the graph. Why is this important? Anybody who's interested in biology or even engineers, you think about fuels, biofuels, stuff like that. Where do we get this stuff from? We're trying to get it from grass and from plants and from old waste from farms. A lot of this stuff involves breaking down carbohydrates. So a carbohydrate, for example, here, if you're taking glucose and you'd treat it with sulfuric acid, you can produce this. This is a carbocation. You'll see a lot of this next semester when I talk about pharmaceuticals that are developed around this structure. The glycosyl carbocation. It is an SN1 process. This is a good carbocation because of resonance. That's the second term, but it still is a carbocation type process. It needs some help from something electron rich. In this case, we might have some methanol in here, and we can trap that methanol as a nucleophile, and away we go. So these processes are very straightforward but fundamental, and will show up an awful lot as we work our way through 2 terms. There is the graph for a typical SN1. Again, those flashcards I put together, everything's together in one file. It's only about 12 pages. And it tries to just pull out the important features of each of these reactions so you have something combined and condensed in front of you. In the SN1 process, we can prove through various experiments, such as the kinetic one we just did by adding more of the nucleophile that didn't do anything, that in the SN1, the leaving group comes off first. That gives us a carbocation. The nature of that carbocation will dictate whether this is possible or not. So tertiary carbocations, no problem whatsoever. Secondary carbocations, not so bad, not so good, but okay. Primary carbocations, no. Methyl carbocations, no, because they just don't get the help from hyperconjugation. And they can go someplace else. They can do SN2 reactions. So we get this balance between which pathway we're going. We have a starter material here, the leaving group, and the substrate with the leaving group, and it's coming off, it's breaking off. We'll be able to draw these transition states quite quickly. At the top of that barrier, this thing is almost broken, it's almost collapsed. and then it gives a carbocation. Don't forget, this is a reactive intermediate. It's actually something that does not get isolated. We can measure it, that it gets formed. It does not get isolated, but then it goes someplace else. And the height of that horizontal there tells you that this is the rate determining step. It's quite a high barrier. And this reaction barrier here, the second one, is fast. It's like a roller coaster. It takes forever to get up there, but once you get up there, boom, you're home. That's it. That's all it is. So most of that reaction, essentially, how fast it goes is dictated by that first barrier. And in that first barrier, where's the nucleophile? Not involved is the answer. It's not involved. The nucleophile comes in the second step, in which the nucleophile attacks that carbocation. So that's unimolecular. Tricky. Difficult to keep a track of. Yeah, especially when you've got other classes, like physics or genetics or whatever. So come and ask some questions when you need them answered. Sarah.
Okay, so if it's tertiary, it's going to be S1. If it's primary, it's going to be S1.
Yes, and that's a fair comment. Secondary is a nightmare.
It's not necessarily.
Secondary is Halloween. Right? It's when 5,000 snotty kids come to your house and you don't want to listen to them. It's horrible. We'll deal with it in a minute. So there's the answer to that question, really, that slide. In the SN1 process, you're not going to get SN1 with a methyl group. Why not? Because the carbocation you're asking to be produced is way too unstable. Why? Because it has no hyperconjugation. As you move to a primary system, they don't do SN1. Why not? Because they can do SN2. They have that alternate pathway because they're accessible. They don't have to rely upon hyperconjugation because you don't need to form a carbocation, because they can go someplace else by being attacked because they're accessible. And then I can see here the secondary. Now we're getting to this sort of nightmarish scenario where it will depend upon the conditions. In the presence of a good nucleophile, maybe you'll do SN2. In the presence of a poor nucleophile, maybe you've got time to do SN1. That's a lot of Friday's class. So here is sort of definitely to the left here, SN2, to the right here, SN1. And this graph is showing you the relative rates of SN1 reaction, tertiary by far the best, secondary okay, primary no, methyl definitely no. So we have a change. Around these secondary systems, there seems to be a change in what can happen. And these pictures are just showing you, Haldeman, that in the methyl carbocation, there is no help at all because there are no neighbors. All of the electrons in that molecule are already associated with that central carbon. There are no extra bonds around to help out. As you move to a primary system, you get some help, but not enough. Secondary systems, you can get enough help to make a difference. It can form. Tertiary system here, definitely. They will form. And since tertiary systems can't do SN2, they'll have to do SN1 instead. So we're getting a shift between the two mechanisms. In terms of secondary and tertiary, this is just an extrapolation from the SN2 process. This is showing you that the tertiary system is faster because this is easier to get to. This is a tertiary carbocation. This is a secondary carbocation. It's higher in energy. You have to understand why it's higher in energy, the answer being because it's not as stabilized by hyperconjugation. So the SN1 in a secondary substrate is slower than the SN1 in a tertiary substrate. Why don't we draw graphs for primary and secondary? Why not even bother? They don't do this reaction. They don't need to. They have someplace else to go, which is the SN2. A lot of people are looking very nervous now. I don't know why. We've all been keeping up. We're all ahead. We all come to class. At least you people come to class. Imagine not coming to class. Okay. So somebody alluded to before, I think Colleen, about why wasn't the chlorine drawn on the other side of the molecule? Well, the answer simply is because it's not an SN2. If it was an SN2, we'd have to show inversion because that's what happens. But this is the SN1. And what happens is something very different but very useful. In the SN1, we don't get inversion. Okay? We don't get the major process being inversion. What we do get is a different stereochemical change. So what I've got at the left here is a tertiary alkyl halide, which is chiral. That is definitely chiral. And when this thing breaks apart, I produce a carbocation. So this is, the lobe is there for a reason, to show you the direction of attack to the next piece. But that's the rate determining step, so that's slow. And I'm left with a carbocation here. And that carbocation has 3 different things attached. And it's flat. So I'm going to use this word for the first time. And you'll see it again and again. This is said to be prochiral. And all that simply means is it's flat and it can become chiral. If you bring a fourth different thing in, it can become chiral. So that carbocation itself now is the electrophile in this system. It can be attacked, and we've got to worry about where it can be attacked from. If these things are genuinely flat in the same plane, what is the relationship between this side and this side? They should be the same. If that carbocation is definitely flat and all those groups are planar, the left-hand side, the right-hand side, or the top or the bottom, depending upon how you want to hold this thing, are the same. So now I have a choice. My chloride, in this particular example, is my nucleophile. In the second step of the SN1, this has to come in now and attach to this molecule. What are the chances of attack from there versus the chances of attack from there? The same. They are the same. Because both those sides of the molecules are the same. So how much of these products should I get, theoretically? 50-50. I should be getting 50% of this and 50% of this, if this is true. A lot of the time it is, some of the time it isn't. That produces what we call a racemic mixture. 50% of one isomer, 50% of the other isomer. Give me a word that describes the relationship between that molecule and that molecule. They are enantiomers. Good, we picked something up. They are enantiomers. Now, if I tell you the alpha D of this guy is plus 61, what's the alpha D of this one over here? Minus 61. And if I have equal amounts of both of those things in there, what's the overall alpha D? 0. Good. Okay, alpha D equals 0. That's a big clue. SN2 reactions gave you a number because you got R or S. You didn't get both. In this reaction for the SN1, you get both. And they cancel each other out for the most part, and that gives you 0. So if your alpha D is a 0, it was probably an SN1. If your alpha D was a number, it was probably an SN2. And you can use that piece of information now to actually start solving problems. So this slide will keep you up. Okay, that slide is important. It's, I think, more advanced and more complicated than the SN2 process, but it needs to be handled well. I'm going to do this to totally confuse you, and then we'll break and come back on Friday. But I'm into 53. I've got 40 slides left. I reckon I can get this done Friday and a bit of Monday, and then be into chapter 8 next week. Are we ready? Hold them and you're into this, aren't you? You've got your arms folded. Yeah, it's got to work. Let's do it. This is a nice slide to finish off with for today because we've introduced some interesting concepts that are more advanced than we've seen. But it also tells you about reality. Do you always get alpha D equals 0? Not necessarily. It might be close, but it might not be quite there. Because in this example, trying to show a tertiary alkyl halide, the leaving group breaks off. This is important. Everything we say is important, but this is important. There's my carbocation. As soon as this bond is broken, where is my leaving group? Has it disappeared? Or where is it? It's still there. It's to the right of that molecule. And what does this guy have that this thing wants? Electrons. So should this be reversible? I would think so. Okay? Reversible. Now, we have a nucleophile waiting around. In reality, on Friday, what we'll say is we have lots of nucleophiles. We want to try and swamp out the leaving group. So we have lots of the nucleophile around, so statistically, it has a better chance of attacking. But there's always going to be that possibility of this thing being very close to this side of the molecule, and that can lead to a problem in the outcome. So if I think about this, and it's a leaving group and it's not small, where does the nucleophile have a better chance of attacking from if this thing is right there? From the left or from the right? From the left. So as it shows you on this slide, quite often you get 50% what looks like inversion, because the nucleophile came from the opposite side that the leaving group has broken off. The leaving group has gone, it's broken off, but it's still there momentarily. So the nucleophile has an easier time coming in from the left. And if the nucleophile can beat the leaving group over on that side, I get this other one, which is the retention configuration. So you don't always get 50-50. On my exams, you will. On my exams, I'll always tell you get 50-50. But many of you have put yourselves into this idea of pharmacy school, medical school, graduate school, job, stuff like that, and you need to understand the little details so you can be competitive. So I'm going to leave it there. You go to look about that, come and ask some questions, and we'll get back to it on Friday.